Team 24 and our topic is on data distillation for business decisions. For the agenda today, we'll first talk about our problem statement. Then we'll show our approach and the subsequent results and finish with our discussion. With the rise of the big data phenomenon, deep learning has become the most popular way of exploring data behaviors as well as modeling. However, with growing data sets, as more data are collected, it can cause longer training time as well as high computational cost. While many researchers focus on the efficient algorithm and state-of-art models, some devote themselves to solve the problem by reducing the size of datasets while keeping the results comparable. In this project, we decided to focus on the latter part of this problem, which is the data distillation. Our team experimented with quantitative input influence, or in short QII, to effectively reduce the data size of 2019 American Community Survey measures to the 2019 ACS dataset and reduce the number of data while keeping comparable model predictions based on the outcome feature important. The ACS dataset comprises of detailed U.S. population and housing information for the year 2019. It provides information regarding occupation, educational attainment, home ownership, and other personal information. The dataset consists of around 3.2 million data points and 288 features in total. In this project, we chose the feature PINCP, which stands for the total person's income, as our label, and use the rest of the features as predictors. In our comparative approach, we perform data pre-processing for both methods, which includes eliminating features related to income for collinearity or removing rows with age less than 16. To establish our baseline model, we chose a simple MLP with 2 hidden layers. We subsequently added SVD to improve the accuracy of our evaluation metric. For both methods, we use the MSE loss function, and our evaluation matrix is the coefficient of determination R². Our distillation method uses QII, which stands for quantitative input influence. It helps to measure the degree of influence of inputs on outputs of the system. The QII method is based on the Shapley value evaluation. Shapley score is one way to distribute the total gains of the inputs with the assumption that they all collaborate. To run the QII, we divided our whole dataset into 3 clusters based on their income level. After running the QII analysis for 40 times, we can see that it returns a Shapley value vote distribution over each feature. We can see here as an example where on the left the feature exhibits close to a normal distribution, which suggests that there is great variability in the feature based on the label value. In contrast, the one on the right provides no additional information. The left is the one that we desire to keep, and the right has no meaning, which is the one we want to ignore. Subsequently, we also plotted the Shapley score distribution over all the features. Since we want to focus on the positive Shapley score only, let's focus on those. We can see here the features that contribute positively to the label value for each cluster. It should be noted that some features are overlapping amongst the different clusters. Unfortunately, we did not complete the next part of this analysis for this project, which consists of the cluster stratification strategy. However, we do have some preliminary experiments that will be discussed in the following slides. We first established a baseline using a simple linear regression with about 200,000 points, which yielded an R2 score of 0.62. Subsequently, we experimented with different activation functions and scheduler to yield different results, as you can see on the slide. The best results is with the MLP3. However, we decided to keep the MLP5, which has exactly the same amount of feature as our QII analysis. For the stratification strategy, we used 1 cluster and 1 QII measures over 50,000 points. It yielded a score of 0.55 after 100 epoch. Alternatively, we also measured the validity of our QII measures using the whole dataset and also performing a MLP, which yielded a result of 0.59 after 100 epoch. Although the initial results of our experiment may seem to suggest that QII measures is not an effective strategy for data distillation, however, it should be noted that there are many shortcomings to why our experiment did not run as intended. For instance, due to computation and time limitation, we reduced the size for QII analysis to 10% of the whole dataset. For similar reason, we made the assumption that all occupation contribute to the prediction of the income label and did not run them through the QII. As for the stratification strategy, since in the bottleneck of data processing, which takes more than 10 hours to process about 100,000 points, the small amount of data we have may not be representative of all the data. Lastly, some QI measures are only influential when acting together in a set. Thus, sampling based on selected QII may not improve the results from the original model. In conclusion, QI has the potential to be an effective methodology for data distillation. The hypothesis of using QI lies in its potential to be applied to different data sets, thus saving significant amount of time and resources. This implies that deep neural network training on distilled data sets will be more time and resource efficient. More work in the future needs to be done to properly stratify the data sets using the QI measures to verify this hypothesis. Thank you for watching, and a final special thanks to Joseph Conan for his kind supervision.